Dr. Jongho Lee is professor at the Department of Electrical and Computer Engineering in Seoul National University. He received his Bachelor of Science from Seoul University in 1998 and his Master and PhD at Stanford University in 2007. He worked at the National Institute of Health as a research fellow and then at the Department of Radiology at the University of Pennsylvania as assistant professor. In 2014, he moved back to Seoul National University to join a faculty position. He has been active in international societies such as ISMRM, where he recently gave a plenary talk in 2021. I would like to particularly thank him for giving this talk today, since it is currently about 2 a.m. in the morning in Seoul. So I'd like to applaud his big commitment to share his work with us today.
There you go. So thank you very much for giving me this opportunity to present this work. And that was very nice introduction. Well, it's 2:30 again a.m. in Seoul, which is okay time for me to stay up late, since I usually stay up late. The problem is I have this sore throat, so I may keep drinking, my tea or my water, or so bear with me if I do that. So the topic that I will talk about today is advanced susceptibility imaging, and that's focused on a new technology called Chi separation that I developed from my lab. And let's begin. But before we really go into the details of the technology, let me briefly introduce some of the other technologies that I've been developing in the lab. One of them is this neuromelanin imaging that has become a new powerful contrast that you may be able to visualize the neuromelanin in the brain, especially in the substantia nigra or locus coeruleus. What we have developed is a new approach that is vendor neutral, so you can set it up in any of the vendors by utilizing this sandwich saturated flow saturation pulses or regional saturation pulses, such that you can get a high contrast and high reliability for neuromelanin contrast imaging. And that's the first one that I want to just briefly introduce you. The second one is so-called SMWI. SMWI is a tool that allows us to visualize this swallowtail sign or nigrogen 1 structure that has been shown to be sensitive to the Parkinson's disease. I believe these two topics will be covered by our next speaker, Stefan, who is the expert in the field in the Parkinson's disease, that really like his talk. So I'm very excited. Although he may not use exactly the same technology that I presented here, but he will give you different result of it. So I'm very excited about his talk as well. The one that I will talk about today mainly is this Chi separation technology, and that's the main topic of my presentation. And this new technology will allow us to generate this high contrast, high reliable contrast of the negative susceptibility and positive susceptibility maps. And the negative susceptibility map largely corresponds to the myelin concentration in the brain, whereas the positive one goes to the iron concentration in the brain. So I believe this can be a very powerful tool that we can use it for the exploration of the brain pathology as well as the degeneration as we get older. So with that, let me start with the basics, the QSM, as Chi separation is the advanced version of the QSM. And if you are not familiar with it, this can be a very good introduction of the technology. QSM is a technology that has been developed about 15 years ago. And so that's a quite recent technology for MRI. And it allows us to measure the magnetic susceptibility contrast in quantitative manner. as we all know, magnetic susceptibility is a property of material. So we can utilize this technology to measure the susceptibility of the brain. For example, we can measure the susceptibility of globus pallidus, or in the white matter, like splenium of the brain. Or you can also measure the susceptibility of hemorrhage, as we know that it has a large cluster of the iron there. So we expect it to have much higher positive susceptibility as compared to the rest of the brain. Also, when it comes to the disease like MS, we know that there is a demyelination. And in some cases, we have the concentrated increase of the iron in the rim of the pathology or lesion, so that we can utilize the QSM as a way of visualizing or characterizing lesion types in MS. So the technology is quite neat and exciting. And when it comes to the physics of the QSM, that's another thing that we, at least for me, like as an electrical engineering, it's one of the very fascinating tool or the physics that is in the QSM. The thing about this magnetic susceptibility is once you have a point source of the magnetic susceptibility within the visual field, the result that we get of this point source is this type of field perturbation. And that's the 2D representation. And if I show you the 3D representation, this is the shape. We have like tube, and there are two balls up and below the tube. So that's a typical field perturbation pattern, and that's what we call as dipole pattern. And again, the beauty here is point source goes to the dipole pattern, and each point source will generate the dipole pattern, meaning that there is a convolution relationship between the source and the dipole pattern. So you can simplify the relationship as shown here. Once you have, if you think about a brain that has certain susceptibility distribution, what we can measure from MRI, especially the phase of the GRE data, is the local frequency shift map or local field distribution map shown here. So the relationship is now your source, which is the susceptibility distribution, convoluted with the dipole pattern. And that's the result that you can measure from your MRI. And all we have to do is to reverse the process. First, you get the local field map from your GRE phase, and then perform the deconvolution of this dipole pattern. Then you finally get the result that you wanted, the source image, which is the magnetic susceptibility distribution of the brain. Well, for anyone who took the signal and signal systems class, we know the relationship between the convolution. If it is LTI system, then we can do the Fourier transform on each of it. And then this convolution becomes multiplication. And there comes the Fourier transform of the dipole pattern. And the relationship holds, so now the deconvolution becomes division. And then there comes the dipole pattern in K-space. The problem is this dipole pattern in K-space contains zeros along these lines. So that's so-called zero cone locations. And if you divide something by zero, that's not a good thing that you can have. So there has been solutions that we have been developing over the last 10 plus years of time. The best way of getting the result is more data sets so that you can transform this ill-conditioned problem to a well-conditioned problem. So the idea is you acquire the data in this upright position, and then you rotate the brain and acquire one more data set. You rotate it again and acquire one more data set. Roughly, if you have 4 to 5 orientations, or more, then you can have you can retransform, or you can transform the ill-conditioned problem to well-conditioned problem, and that's what we call as Cosmos solution of the QSM reconstruction. This is a technology that allows us to get a gold standard result, but it's not something that's practical. You cannot really have your patient, rotate the brain multiple times in a scanner. I often joke that this is something that you can do if you are a graduate student and is a co-author of the paper. On the other hand, as an electrical engineers, we all know how to solve this type of ill-conditioned problem by utilizing regularization. So there has been a lot of efforts of fixing this problem, single orientation. And that's practical, but it always contains some errors, so-called streaking artifacts in the QSM result. Well, we are now living in the world of deep learning, and deep learning has been shown a great deal of progress in solving these inverse problems. And it really works well, especially when you have these expensive gold standard labels available for you. And QSM is exactly that type of problem. So if you think about the QSM, we have, as I mentioned before, we have this multi-orientation Cosmos data set that we can generate high quality gold label or gold standard labels, which we can use them to train the network. So single orientation as the input, and Cosmos gold standard label as the label, and then we can keep training the neural net so that it learns how to process the single orientation input and generate these gold standard quality maps. And that has been done a few years ago from my lab and in other labs as well. And that technology from my lab is called QSMNet. And that result is quite interesting and, to some extent exciting, because these two images at the upper row shows the conventional reconstruction containing streaking artifacts at certain angle. And that's the multi-orientation Cosmos reconstruction at the bottom right. Whereas, bottom left, you see this QSMNet result that only uses a single orientation data set, but still does not have any artifact. Oops, sorry. Let me try to show. Oh, there we go. Does not have this streaking artifact and has the quality of the Cosmos result. So this is something that we can do with the deep learning, and that's quite exciting to see the result. And with that in mind, we can move on to the next topic, or the main topic of Chi separation, which is susceptibility source separation technique toward the iron and myelin mapping. So if you think about this will be pretty busy slides, so let me walk you one by one, and still it will be pretty challenging to understand it. So if you think about your imaging volume, and within the imaging volume, you only have a voxel that contains susceptibility source. And here we have a bunch of susceptibility sources that has the same susceptibility values and the same size, like shape. And so we call it as homogeneous and isotropic susceptibility sources. And then we are in the, you have to assume that we are in the static dephasing regime as well. And with that, if you put the voxel within the B0 field, then that's the field perturbation you will get, and you can measure from MRI. And if you see this field perturbation far away from the voxel, and that's the field perturbation outside of the voxel, which is something that you can measure directly from your MRI data sets. Well, when it comes to the T2 star decay, because of this microscopic field perturbation, now you have not only T2 or R2, you also have this R2 prime that creates additional or accelerated decay. That's what we call as T2 star. It's the combination of the T2 and T2 prime. So here we have the two equations that we already know from the previous literatures. What happens if we change the sign of these susceptibility sources? And the result is pretty simple. Nothing changes in the R2 prime or R2 star decay. It's exactly the same, only the sign changed. And that's the reason why we have absolute value here. Your bulk susceptibility, you have to do the absolute value of it so that you can measure the R2 prime change. But what really changes is the sign of the field that is outside of the voxel. So now if you look at these second equations, it doesn't have this SO value so that we can retain the sign of the susceptibility. For us, the real question is what will happen if we combine these two voxels and generate a result that generate a voxel that contains both positive and negative susceptibility sources. And then that will be our microscopic field perturbation. And the result is we no longer has field frequency shift outside of voxel as they cancels out each totally if you are at the static dephasing regime. And again, you have to satisfy these conditions to do it. When it comes to the R2 prime, that's additive. So you have the double the R2 prime value as before. That's our theory that we have that are directly derived from the previous, previous equations. And then we also have this solution that by combining these two equations, we can separate this positive susceptibility from negative susceptibility, generating the two maps. And the result can be generated in multiple different ways, just like the QSM reconstruction. So this is the overall pipeline of the chi separation. So first we need to measure this multi-echo GRE so that we can generate this R2 star and frequency shift map. Another one that we need is this multi-echo spin echo data so that we can measure our R2. And then by subtracting these two values, we get R2 prime result, which is the core part of the susceptibility measurement. And then we have these two inputs as with these two maps as the input for the chi separation, and the algorithm generates this positive susceptibility map and negative susceptibility map. And again, we have multiple different ways of generating these two maps. And the first one is just utilizing this single orientation data set and use some of the regularization like MEDI regularization that is popular in QSM reconstruction. And we can generate this positive and negative susceptibility map. We can acquire multiple head orientation data sets and then again generate the better images. Of course, you can go for the deep learning as I introduced in the previous slide. And in this particular deep learning method, we can also get rid of the need for acquiring R2 data. So here we simply utilize the multi-echo GRE data so that we no longer have to suffer from the data acquisition side where R2 mapping is very rare in clinical acquisition. So again, it simplifies the data acquisition, and NeuroLab simplifies the data processing, but you have to understand that there are always some errors in the resulting images, and that's the limitation of the deep learning that you can expect from your process. Anyway, so we try to validate this idea by first using this computer simulation of Monte Carlo simulation. So we designed total 9, cylinders. The first row has different concentration of positive susceptibility sources only. Second row has negative susceptibility sources only. The third row contained both positive and negative susceptibility sources. We mix them together and then generate the frequency shift and R2 prime result by computer simulation. After then, from these two results, we apply the chi separation, successfully generating source-separated result with the correct quantification result as shown on the plot, on the right plot. And then we moved on to the phantom experiment where we designed exactly the same type of the phantom that we have this iron oxide and CaCO3 as a negative susceptibility source and the mixed cylinders. And that's our two measurement, frequency shift, R2 prime. And these are the inputs for the chi separation, and we can successfully separate the positive, negative, and mixed cylinders with a pretty good accuracy as shown on the right plot. And now the question was, the phantom is not our target. Of course, the target is the brain. Now the question is whether this one will work in the brain. The good news is that in the brain, we roughly have two susceptibility sources. The first one is, iron, which is the primarily the paramagnetic or positive susceptibility as compared to water. And then the other source is myelin, which is diamagnetic. And I can say that these two are the major sources of the susceptibility in the brain. In rare cases, you will get copper or zinc as some disease cases. And in some cases, you also get this calcification, which is normally of no interest for the clinical or research-wise. So this first assumption is roughly right. And the second thing, the more important one, is whether do we really need to separate the two so that we can see things, as we know that in white matter it's roughly myelin, and in the deep gray matter it's roughly iron. But in fact, when you analyze the data, you will see that most of the brain contains both sources. So we really need the separation. It will be very apparent by looking at the results at the end of my presentation. So that one, yes, we do need the separation so that we can see the details individually. Another one that we need to have as an assumption is we have to assume that susceptibility is the primary source for the R2 prime and frequency shift, which is again okay assumption, because we have been looking for other sources like exchange that only accounts for about 10% of the total signal changes in the frequency shift. Lastly, we need to have this static dephasing regime hold so that we can have these two equations working for us. Except some areas, we believe roughly static dephasing is okay. But despite all these assumptions that we are fine, there's one last one that is not okay, and which is the assumption of homogeneous and isotropic susceptibility sources. We know that iron has roughly, like ferritin, has roughly spherical shape, and its diameter varies from one to another, but they have certain ranges. But comparing that to myelin susceptibility, which is, has this molecular as well as microstructural shape, and it is elongated structures in both ways. So they are not exactly homogeneous or isotropic. And also in myelin, we know that there is a susceptibility anisotropy as well. So the assumption is a little bit inaccurate for myelin. So we have to suffer from some errors generated from these effects. But having said that, our first question is, why do we just apply it and see what the results look like when it comes to some brain specimen that has known structures in the myelin and iron. And this is our first result that shows the positive and negative susceptibility maps. And this is iron image, and this is myelin stain result. And if you compare this kind negative map with myelin stain, it's quite remarkable that despite the limitation of the technology, you can see this line of Ginari in the visual cortex, the V1, that is known to exist in the histology that are shown here. Another thing that's exciting is this white matter fiber bundles has different contrast, and that contrast matches to the myelin density of these fibers. The same thing goes for this chi positive map and iron image on the left, where you can also see this line of Ginari, and that has been known in the iron map that shows the increased iron deposition in the line of Ginari that corresponds to the result of chi positive if you look at this line here. And the same goes for the white matter fiber bundle as well. So that tells us that you can, the method chi separation gives you the anatomical information that you are looking for. We went on and began to look at different areas of the brain, and this is the thalamus with globulus pallidus region, and internal capsule is there. And if you look at the details of the structures, it's quite exciting that you can see a great details of the thalamic nucleus that matches to the histology result, and that's the histology of myelin stain. So that's another very exciting result, that you can use the technology for some uses that you may be excited about. And when it comes to the in vivo, you can see a lot of similarity from our chi separation result to the literature images of iron stain or myelin stain. And of course, there are artifacts. For example, large vessels, they have a lot of deoxyhemoglobin. So you are supposed to see it in the positive susceptibility map. But large voxels that usually go beyond the voxel size or comparable to the voxel size, they no longer satisfy the static dephasing regime condition. So they ended up with showing up in the negative susceptibility map. And that's one of the large artifacts that we see in the result. And here's one of the results that I really like. And here's the myelin histology result. And that's the ex vivo chi-negative map at high field strength. And that was acquired with 10 hours of scan. And this is really the 3T result that we can acquire in 20 minutes of scan time. And that's in vivo result. And what we can see here is the laminar structure of globus pallidus that you rarely see them in at least at 3T. At 7T, you may be able to see them somewhat, but it's pretty difficult to see it at 3T. But with this new technology, you can visualize them. So again, despite the limitations, there are good things that you can use it for. And that application is something that you may find the technology interesting. Another study that we perform is looking at this cortical profile, or we begin to call it as cortical depth-wise profiles. So we chose, like circus and then fundus of the circus and averaged the profile along the depth and then plotted here. Here is the cortex, and that's the gray and white matter boundary, and that's superficial white matter, and there is the deep white matter. And you can see this positive susceptibility profile, negative susceptibility profile. And we also compare them with the QSM profile and R2 star result, and at two different circles. And if you see the result and compare it to this Kirillina paper that are recently published, and that's from the temporal lobe of the temporal lobe and using the histology, and you can see that iron peaks right after the cortex, and that shows up in our result. And the myelin peaks at the deep, deep into the superficial white matter or deep white matter, and that's also consistent in our result. So again, it is pretty exciting to this result. And one thing that I want to point out at this particular example is the fact that QSM and R2 star peaks at different locations, so they may not, carry exactly the same. They may not be exactly the same as chi separation result. So that seems to make sense to me, at least, because QSM or R2 star, they are both affected by the myelin and iron. So you don't expect them to explain one of the contrasts that you have in the hand. We also did, MS patient, study looking at this so-called iron rim lesion, where QSM can identify it, but does not really tell you whether you can separate, whether there is a demyelination or not. But chi separation tell you, okay, at the edges, you get this iron rim, and then at the core, you get demyelination. I believe it's something that you can use it for additional categorization of the lesions in MS. And that's our final result of the high resolution 3T in vivo result. Again, that's 0.7 millimeter isotropic voxels at 3 Tesla, again, 20 minutes. And that uses a lot of deep learning reconstruction as well as processing. So again, there has to be some errors. Deep learning always comes with some limitations. But again, it tells you a lot of details that you probably expect to see from anatomy. One thing that I really like is if I can stop this video clips at the location that I wanted. So let's try to stop it now. Okay, there we go. Here is the so-called, the inverted omega sign of the hand knob. And we know that this hand knob has increased iron as compared to as compared to the sensory cortex. And that's feasible here in both ways. And also, if you look at this negative susceptibility map, around the hand knob, the white matter has higher, myelin concentration as expected. And I believe that's something that you can see in the myelin water imaging as well. So let's move on. Of course, this is not the only thing we do in our lab. There are other labs who are developing the technology as well in certain different directions, and also utilize it to explore some other disease. Especially the MS is the good target to start with, as we know the lesion characteristics, and high separation is an easy way of developing a more information or gathering more information from MS lesions. So people are very excited about this new direction, and the research is on the way. So with that, let me summarize my presentation. Again, the high separation is a new tool. So it is an advanced QSM tool that generates a positive and negative susceptibility map. I've been saying about these assumptions because one has to be very clear what we can do and what we cannot do with the technology, and there are always limitations of it. So I'm very cautious about saying the positive susceptibility map and equating to the iron map. By the way, this is something that I learned from a lot of people, and that's this kind of labeling has to be very cautious. So I try to stay with the positive susceptibility map, and it can be what's the right word for it? It can be just a biomarker of the iron. That's imaging biomarker of the iron. Again, the negative susceptibility map is not equal to myelin map, but still it can be a good representation of the myelin, although there are more complications when it comes to myelin because of the orientation effect. We still give you a successful delineation of histologically well-known structures, and when you use, and you're willing to accept the deep learning as the technology, and we can only need the GRE data sets. And now we have this alpha version of the toolbox with a lot of bugs. And if you're willing to debug some of them, then I'm willing to share it with you. With that, I want to thank you for your attention, and also all my students who did excellent work of developing the technology. Thank you very much, and I'm happy to take the questions.
Thank you for this amazing talk. It was really interesting. So Olivier, do we have any question on the chat?
Yeah, there's one question in the chat from Dr. Jing Chen, who asks, what's your recommendation for dealing with B0 inhomogeneities?
That's, largely speaking, if you do the good shimming, you can get a pretty large coverage, including some of the temporal lobe. It's exactly the same as the QSM. So in the QSM, you can get a pretty good coverage to the temporal lobe. So roughly you get the same result there. There is no additional processing that we utilize to get a better result of background field.
Thank you. So Stéphane Léhérécy, you have a question you can ask.
Yes, thank you, Jongho. Very nice talk. I was wondering whether by combining negative and positive susceptibility, you could distinguish Broca's area.
Oh, can you say the last word?
Broca's area, the areas of Broca.
Oh, I haven't tried it. My knowledge of anatomy usually stays with the visual cortex and motor cortex. So I never look into the Broca's area. So I can send you our reconstructed result so that we can see whether we can identify the Broca. Thank you very much.
Thank you. There's one more question in the chat from Chris Taylor, who asks, do you have any plans to extend the model to consider the anisotropy in myelin, for instance, using a tensor-based approach from diffusion imaging?
Well, so, Chunle Liu at Berkeley is doing a similar line of work. He already published, papers or just abstracts on the topic. The challenge is that realistically, you cannot really rotate the brain for the patient. And then, of course, your idea of using the DTI information and combine that or the avoiding this multi-head orientation equation is one direction that that we can go. But the problem of this STI, susceptibility tensor imaging, to the DTI, and if you are not familiar with STI, that's using this anisotropy to find the fiber orientation. Very similar to the DTI, but again, we need to acquire multiple head orientation information. The problem of that is their fiber orientation does not really align well. So there are some similarities and there are some differences. Now the question is which one to believe when you try to extract additional information from the brain. That means your diffusion data may end up with screwing up your reconstruction result when it comes to the susceptibility information. So for me, that's challenging.
Thank you. Very interesting. Maybe one last question from Agnieszka Burzinska. I hope I'm pronouncing that well. So she asks, you demonstrated that chi separation has great anatomical fidelity, both with anatomical structures and in MS lesions. But can you comment on its ability to detect more subtle individual differences in myelin and iron content?
That's something that I really want to do. So if you have a lot of interest, and if you happen to have multi-echo GRE data, that's something that we can run and compare. So we are right now running multiple projects. Of course, some of them are on Parkinson's disease, some are in AD, and also some pediatric data sets, as we know the myelin increases dramatically over the early stage of the 10 plus years of life. And that's something that we are very excited about. And some of the previous presentation using empty set is again very exciting. And my hope is we will be able to see the similar result using our data set. But that's something that we want to go for as the future applications of the technology.
So thank you very much. I think we are going to move forward with the program.